I'm going to be talking about NERJA, which is a new high-performance consensus protocol. And the main idea here is to use clocks that are synchronized in software through an algorithm rather than hardware support for clock synchronization. And this in turn makes it easy to deploy NERJA for a cloud tenant with no support from their cloud provider. NERJA was Jenkins' dissertation work at Stanford, and really he should be giving the talk. I'm giving it instead because he couldn't travel for visa reasons. So consensus has a long and rich research literature going back about 4 decades. And it's also substantially impacted the practice of distributed systems. Yet, despite almost 4 decades of work on this topic, it continues to be a bottleneck in that consensus, when it's part of a larger system, seems to affect adversely the performance of the larger system. So these are practitioner reports drawn from 4 different areas: databases, key value stores, stream processing, and container orchestration, that suggest that better performance consensus would be quite useful. So why is this the case? Why is consensus still so slow? So let's start with the goal of consensus. The canonical use case for consensus in distributed systems is in what's called state machine replication. So here, clients are submitting operations to some kind of replicated service, which is replicated for high availability. And the goal of consensus is for a group of machines to agree on the contents of a replicated ordered log of these operations, where these operations are gets, puts, etc. So the simplest way to achieve consensus is to have all client operations to go through a single replica, which then serializes these operations into some arbitrary order and then enforces this order on all of the other replicas. And this is the basis of the so-called single leader protocols like Raft and multipaxers, where this replica responsible for serialization is called the leader. So at a high level, the workflow looks something like this. The client sends its operation to the leader, which then replicates that operation to all of the follower replicas, which all then respond. And once the leader collects enough responses, called a quorum, it replies to the client with the actual result of the operation. Okay. The problem with this approach is that the leader soon runs out of steam, because for a single client operation, it needs to communicate with multiple followers to send them the operation, and then it needs to receive from multiple followers to receive the responses, and then reply back to the client. Okay, and as the number of clients or the client request rate goes up, the leader soon runs out of steam. So one way to fix this is to use optimism. Okay, and I'll illustrate these optimistic protocols through the example of no paxers, but the pattern is more general. So here, clients directly multicast their operations to all replicas to sort of spread out the load. A proxy could do this on the client's behalf. And here by multicast, I mean either network support for multicast, like IP multicast, or an application library that effectively does multiple distinct unicasts. We use the application library approach in our work, but at this point in the talk, I'm just talking about multicast conceptually. Now, once the replicas get all these operations, they can respond back to the client, assuming the operations all arrive in the same order at multiple replicas. Okay. So in this case, ordering is achieved kind of for free, and the replicas respond directly, and the client considers the operation committed. Now, in practice, things are not nearly as good. So the operations might get reordered, arrive in one order, say get and then put at one replica, whereas put followed by get in a different replica. So the general case is more or less similar to something like Paxos, where the leader needs to step in and actually tell the followers what the arbitrary order it decided on is. Okay. And this example is common to many optimistic protocols, such as fast paxers, spec paxers, and so on. But the underlying assumption for all of these protocols is the fast path is indeed the common case. Okay. Because if not, then there's no point in optimizing the fast path if you're going to keep falling back to the slow path anyway. But what if, thanks to the network that carries the operation within a message, client operations end up arriving at different orders at different replicas? Okay, and if this happens often enough, then you end up just taking the slow path so often that any fast path optimization is negated. So let me show you first why that might happen, and second, how you might fix it. So here's a toy topology, a sender, two switches, and two receivers, R1 and R2. The assumption here is the links from the second switch to R1 and R2 have the same delay. And the point of this example is that there are multiple paths of unequal delay between S and R1 or S and R2. Okay, and those are the three paths between the two switches. The blue path is the shortest, the green curved path is of intermediate length, and the red path is of the longest delay. Now, the presence of these multiple non-equal delay paths causes conditions that allow messages to arrive at one order at one replica and a different order at a different replica. So let's quickly see why that happens. Let's say the sender, as the client, wants to communicate operations A followed by B to both replicas R1 and R2. So there are 4 copies total. It ships them on the wire towards the first switch in that order, and the order is preserved until the first switch. At this point, because of the routing policy, the switch might route A and B over any of the 3 candidate paths to the next switch. And it can so happen that because of the way the routing was done, A arrives before B at R1, but A arrives after B at R2. Okay. So how do we fix this? The answer is to basically take away choice from the first switch in terms of the multiple candidate paths that it can route over to the next switch, and instead enforce control over the routing of messages inside this network. So one way to do it in this case would be to force the path from S to R1 and S to R2 to have the same delay under the assumption that the second switch to R1 and R2 have the same delay. And if you set this up this way, then you could force A and B to both take the shortest path between the two switches. And that way, it's quite likely, but not guaranteed, that A arrives before B at both R1 and R2. Now, a line of prior work has shown substantial performance improvements using this sort of approach relative to Raft, Paxos, and so on. Okay, so our work deals with cloud tenants who aren't able to control routing of messages between their VMs. A cloud tenant is presented a group of VMs which can all communicate with each other by, say, using sockets, but they don't control the paths over which that communication happens. So how do you deal with addressing reordering and increasing the incidence of the fast path for a cloud tenant? So our answer is to use synchronized clocks. And the high-level idea is quite straightforward, which is you hold a message arriving at any particular receiver until it's quite likely that the same message has been received by all of the other receivers. Okay, and this way you equalize travel time between the sender and all receivers. And essentially what's going on here is you add a little bit of latency to the fast path, but in the process, you reduce incidence of reordering, and that increases the fast path frequency. Okay, so you add latency to fast path, but also increase its frequency. And in this context, I'll talk about a new multicast primitive based on synchronized clocks called DOM, and the NRJA protocol that leverages this primitive. So why is this happening now? Over the last several years, there's been a bunch of academic and commercial offerings that provide high accuracy clock synchronization as a cloud service, and that allows us to revisit classical distributed systems questions armed with synchronized clocks as a primitive. And the main design principle here, and I'll come back to this once I describe the NERJA protocol, is that we're using clock synchronization to speed up consensus, but the correctness condition of linearizability isn't tied to an assumption on the max offset between clocks. Okay, so let me get into the primitive itself. So DOM is a kind of multicast, so you would naturally expect a sender and multiple receivers. They're all synchronized to the same clock. Now let's say at synchronized time 3, the sender attaches a deadline to the message that it wishes to send to all of the receivers, and then creates a copy, one for each receiver, and sends it out. Now these messages arrive at the receivers at various different times. Okay. And none of this can be predicted because the network is not in the sender's control. Okay, the point is message arrivals are unpredictable. Now at time 9, all of the receivers simultaneously process the message. And we add an additional constraint that once a receiver processes a particular message, it's not allowed to go back and process a message with an earlier deadline. So once it processes deadline 9, it can't go back and process 8 or 7. And I should stress that DOM is best effort, in that if a message doesn't make it before the deadline, it's no longer DOM's problem. If a message doesn't ever make it at all, again, it's not DOM's problem. This is why the NERJA protocol that builds on top of the DOM primitive has a slow path to handle all of these cases where the DOM primitive essentially fails because it's best effort. So how do we estimate deadlines in DOM? We have background probes to get the one-way delay between the sender and each receiver. And we take the send time plus the maximum of these one-way delays to get the deadline. And the main trade-off is you can be extremely conservative by estimating one-way delays at a very high percentile, and you would significantly reduce the reordering and increase the frequency of the fast path, but your deadline would be really high, so your fast path latency would be quite high. It wouldn't really be a fast path after all. Okay, so how effective is DOM at reducing reordering? So to answer this, we first set out to define a reordering score. Okay. And the setup for it is as follows. We have 2 receivers and multiple senders multicasting their messages to both R1 and R2. Each message is a different color, and each receiver receives a sequence of messages. We're assuming no drops. So here's a time sequence diagram. And let's say we have 4 messages with 4 colors received at both R1 and R2. Now with this setup, we're ready to define a reordering score. We first assign each color of message a sequence number based on the order in which it arrived at R1. And that gives us a sequence 1, 2, 3, 4 by definition. We use these sequence numbers from R1 to determine the R2 arrival sequence, which looks like 1, 3, 2, 4. Now, we look at the longest increasing subsequence in R2 and get its length and plug that in to compute the reordering score, which turns out to be 25% because the longest increasing subsequence is 1, 2, 4 or 1, 3, 4, and that gives you 25%. As another quick example, if R1 and R2 had identical arrivals, then the reordering score would be 0. So that kind of checks out. The main thing to take away is higher score is more reordering. Okay. So we went out and measured this on Google Cloud, and there are 2 main takeaways here. First is message reordering does happen, and the implication of this is if you had no DOM turned on, just over 40% of client operations that were not commutative with each other would end up taking the slow path. And second, no matter how conservative we are with estimating DOM at higher and higher percentiles, there's always going to be some amount of reordering because it's a best effort primitive. So we need a slow path to handle all of these residual corner cases. Okay, now let me switch to the second part and describe NERJA in some detail. This is a highly simplified explanation. So let me first start with the fast path where all messages arrive before their deadlines. So let's say we have two clients, blue and orange, with deadlines 10 and 12, sending to 3 replicas. So 6 message arrivals total. They all arrive before their respective deadlines. And by t equal to 9, they've all arrived. Now the replicas wait until t equal to 10 to process the blue message, at which point they respond to the client, which considers it committed as long as everything before the blue message, meaning everything that has a smaller deadline than the blue message, has also committed. And that's because the replicated ordered log is ordered by deadline at all of the replicas. So you can only commit deadline 10 if the stuff before 10 has been committed. Similarly, we wait till t equal to 12 and then commit the orange message, assuming there was nothing in between blue and orange. So the fast path is straightforward. Let's look at the slow path. Now, any number of things could happen here. I'm just picking one example. Let's say client one's blue request, blue operation, showed up before its deadline, and the leader responded, but it didn't make it to its followers before the deadline. Okay. So client one can't yet consider blue committed because it doesn't have enough responses because it hasn't heard from follower 2 and follower 1 yet. Meanwhile, client 2's orange operation makes it to all of the replicas properly before its deadline, and they all respond, but client 2's operation can't commit yet because the orange operation's deadline 12 is greater than the blue operation deadline 10, and remember that we're ordering the log by the deadline. Okay, let's also say that by t equal to 13, the other blue messages have shown up on follower 2 and follower 1. So essentially, we're stuck now. The blue operation needs to be committed before the orange operation can be committed, but there's no easy way to commit the blue operation because the other 2 messages for blue arrived too late, and it's no longer DOM's responsibility when something arrives too late. Okay. So this is where the leader needs to step in for liveness and to make progress in the protocol. So the leader essentially steps in and says that we should be committing blue first and tells the followers that, at which point they commit blue and then they're ready to commit orange as well. Okay. I'm simplifying quite a few details, but the main thing to take away from this fast path versus slow path distinction is that the fast path is really where synchronized clocks matter, because that's where deadlines need to be accurate estimates of one-way delays so that messages arrive with high probability before deadlines. If for whatever reason clocks are poorly synchronized, and this does happen in practice, then we can always fall back to the slow path, which is still correct, but it's just slower. So this way, we don't need to make any assumptions on the max offset between clocks for correctness. Okay, so we evaluated and compared against 3 baselines that I'll show you here. There's a few more in the paper. And this was the workload, and we had 2 versions of NERJA, one in which the client directly performs the multicast and another in which the work of multicast is offloaded to a proxy to save client CPU. And these were all run in Google Cloud in a single data center. And to be clear, we don't expect NERJA to provide benefits in a cluster with control over the network. Okay. Our point here is there are realistic scenarios like the ones seen by cloud tenants where there is no such control over the network, and it's in those scenarios where we expect a benefit. Okay. We have a technical report with many more evaluations and several more baselines. So let me briefly describe our evaluations. The first experiment compares protocols that leave the final copy of the data structure in memory And there's really two main takeaways here. Nerja improves performance because it reduces the amount of reordering relative to an optimistic protocol like fastpaxers, and relative to a system like multipaxers, which does quite a bit at the leader. Nerja improves performance because it's an optimistic protocol where the leaders and followers participate and share in the work much more equally. And we also see that the proxy increases latency, but ends up saving client CPU, which might be a worthwhile trade-off. Next, we compare against the well-known Raft protocol. Here, we persist to disk just like Raft does so that we have an apples-to-apples comparison. And the main takeaway is that, again, we improve performance, but the absolute numbers are much worse because we're persisting to disk. So to wrap up, I want to leave you with a simple and general idea that applies to accelerating consensus much beyond the Nerja protocol, which is just an example. And the idea is you synchronize client and replica clocks. A client sends out its operation as a multicast to all of the replicas and attaches a deadline based on the one-way delay between the client and the replica, which you can do with synchronized clocks. Now, replicas delay processing an operation until the deadline and process multiple operations in deadline order. Now, this approach works because it essentially increases the frequency of fast paths by adding a little bit of waiting time and increasing the fast path latency. Okay. As part of future work, we're integrating this with larger scale systems to study end-to-end benefits. The code is available here, and please visit our poster. Thank you.